Today we are going to talk about how to find the response of a general RLC circuit. So we've talked about parallel RLC circuits and series RLC circuits so far in this class, but there are some instances where we might have an RLC circuit that doesn't fall into one of those two categories. In fact, that's going to be much more likely the case, is that it won't be series RLC or won't be parallel RLC. And so we're going to need to figure out how to deal with them. And we're going to develop our approach by looking back at what we did for our series and parallel RLC circuits. So let's start by looking at a parallel RLC circuit where we have a resistor in parallel with an inductor in parallel with a capacitor. And we observed that there was a common voltage Vc of t over all three elements. And we could use that Vc of t to express this resistor current IR of t, this inductor current IL of t, and this capacitor current IC of t as a function of this voltage, and we got a second order homogeneous differential equation given here. The second derivative of the capacitor voltage with respect to time plus 1 over RC times the first derivative of the capacitor voltage with respect to time plus 1 over LC times the capacitor voltage with respect to time is equal to 0. And we found by solving the characteristic equation that this differential equation gives us, alpha was equal to 1 over 2 RC and omega naught was equal to the square root of 1 over LC. Now, if you'll notice, I'm going to call this coefficient right here B, and I'm going to call this coefficient right here C, because that would be the label of the coefficients in our quadratic equation. Okay? Alpha is really nothing more than B over 2. And omega naught is nothing but the square root of our coefficient C. Now, if we look at our series RLC circuit, where we had a resistor in series with an inductor, in series with a capacitor, all of the elements had an associated voltage drop, and there was a common current IL of t flowing in all three elements, we got another second order differential equation. The second derivative of the inductor current with respect to time, this should be squared on both of these, plus R divided by L times the first derivative of the inductor current with respect to time, plus 1 over LC times the inductor current is equal to 0. If we consider this coefficient again to be B, and this coefficient again to be C, we again find that alpha is simply B divided by 2, and omega naught is the square root of C. So, really, all we need to do to be able to apply our table of overdamped, critically damped, and underdamped response equations to any general RLC circuit, whether it's a series RLC circuit, a parallel RLC circuit, or otherwise, is we need to find a second order differential equation and then use the coefficients B and C to give us alpha and omega naught, and then our analysis is exactly the same as if we had had just a simple series RLC circuit or a parallel RLC circuit. In a moment, I'm going to go through the steps of writing the differential equations needed for a general RLC circuit to aid in our analysis. 3, 2, 1, go. This is the circuit that we're going to be analyzing to get a feel for how we will approach our general RLC circuits. I'd like to explain briefly why this is not a series RLC circuit and not a parallel RLC circuit, because this is something that students struggle with a little bit. So during the transient condition, meaning from the time that the switch closes to position B and on, we have this resistor R1 in parallel with our capacitor C, and then that capacitor is in parallel with this inductor L in series with this resistor R2. So it's very similar to a parallel RLC circuit, except that there's no way for us to combine this resistor R1 with this resistor R2 because they're not connected in series and they're not connected in parallel. So this is not a parallel RLC circuit, so we're going to have to use the general approach. One thing that I'm going to do is I'm going to simply add another current. Right now I'm only paying attention to my capacitor voltage, and I'm only paying attention to my inductor voltage, and then capacitor current and inductor current. But to ease our analysis, I'm also going to write a resistor current here, and I'm going to call this I1 of T. We're very quickly going to replace it with some other quantity of interest, but it's going to help us out a little bit. Okay, so at T is equal to 0 plus and beyond, we could apply Kirchhoff's current law to this top node, right? So KCL at the top node would yield I1 as a function of time plus IC as a function of time plus IL as a function of time is equal to 0. I can express this current I1 as VC divided by the quantity R1. And then we'll still have IC of T and IL of T. But I can go one step further here because this current doesn't really help me. And so I can call my capacitor current, I'll just do one more simplification here then, VC of T divided by R1 of T plus C dV by dt plus IL of T. So what I have here is a differential equation that has a 0th derivative term for my capacitor voltage, a first derivative term for my capacitor voltage, and a 0th derivative term for my inductor current. I'm going to try to separate my inductor current from my capacitor voltages, which I could easily do just by subtracting IL of T from both sides, but we'll get to that in a second. I could write a KVL equation around my right-hand loop, and I would get negative VC of T plus VL of T plus R2 times IL of T is equal to 0. And I can express the voltage drop over this inductor in terms of the inductor current so that I get VC of T is equal to, so I'm just moving this VC of T over to the other side of the equal sign, L di by dt plus R2 times IL of t. Oh, sorry, and this is no longer equal to 0 because I moved something around. Now, I have a second equation. This one relates my capacitor voltage to the first derivative of my inductor current and the 0th derivative of my inductor current. So what I'm going to do is I'm going to take the derivative of this equation. dVc by dt will be the derivative of the right-hand side. So that's L times the second derivative of the inductor current with respect to time plus the first derivative now of the inductor current with respect to time. What I have now is two equations, one for Vc of t and one for dV by dt, that I can substitute in to this guy, and I would have this expression entirely in terms of IL of t, its first derivative, and its second derivative. So if I substitute these guys in, what I get is L times di dt plus R2 I of t. That is my Vc of t. I need to multiply this whole thing by a factor of 1 over R1. I'm going to have C times my derivative. So it's going to be plus C times this guy right here. L second derivative IL of t dt squared plus R2 first derivative plus IL of t is equal to 0. And now it's really just algebra getting things to look like they're in the proper form. So for instance, my second derivative term, I'm going to have LC so this takes care of this guy. My first derivative terms, I'm going to have, let's see, so I have an L divided by R1 and a C multiplied by R2 multiplied by the first derivative. So that takes care of this guy and this guy. And then for my 0th derivative terms, I'm going to have R2 divided by R1 and 1. So I now have a second order differential equation, but it's not quite in the form that I need because I need to divide both sides by LC so that the coefficient of my second derivative term is 1. So I'm going to have so let's see. L divided by R1, that quantity divided by LC should give me, the L's are going to cancel each other out, and that's going to be 1 over R1C. For my second term, I'm going to have R2C divided by LC is going to give me R2 over L. And then I'm going to have 1 over LC plus R2 divided by R1 LC times my 0th derivative is equal to 0. And now I have my simple second order differential equation where this is my component B and this is my component C, so that I can say alpha is B over 2. So that's going to be simply 1/2 multiplied by 1 over R1C plus R2 over L. And omega naught is always the square root of C, is going to be the square root of 1 over LC plus R2 divided by R1 LC, if I've done all of my algebra correctly. And from this point on, if I had numbers, I could calculate alpha, calculate omega naught, and then see whether this was critically damped, overdamped, or underdamped, and then approach it just like any other problem. The hardest part of these is developing your second order differential equation and getting it in the right form. And really the only hard part about that is just making sure not to make simple math mistakes. KCl, KVL are perfectly adequate for 99 out of 100 types of these problems. You could also, if you were a little bit of a glutton for punishment, write mesh relationships or nodal analysis relationships. I personally find that using KVL and KCl makes my life a lot easier, but to each their own. So anyway, this is how you would set up a simple general RLC circuit that doesn't satisfy being either a series RLC circuit or a parallel RLC circuit and still be able to analytically determine its response. Thanks for watching. If you have any questions, feel free to shoot me an email.